Hello everyone, this is Anthony Good, amateur radio operator K3NG. In this video series, I'm going to show you how to do multitasking on an Arduino. This is one of those techniques that I think people struggle with when creating programs for the Arduino. I'm going to start out with some easy examples and then go into more complex topics in subsequent videos. In this video series, I expect you to have some basic rudimentary knowledge of the Arduino, like being able to get a sketch, compile it, upload it, test. You should already understand how I/O pins work. You should have some understanding of the serial port, perhaps how to use I2C devices. So this series is for someone who is looking to increase their skills beyond doing things like blinking LEDs or doing things sequentially, writing code in script style. Before we get started, some quick disclaimers. Now that we've got that out of the way, let's talk a little bit about multitasking. I'm going to use this simple example to explain a bit how multitasking works. So what we have here is a room, and within that room we have various things: a bulletin board, TV, a mailbox, and a phone. These little happy guys are people that need to get some work done. But we have a rule here: only one person can be inside the room at a time working. They all carry notepads. In these notepads they write down things that they have to do, things they've done, other information that they need. So they go into the room, they do their work, they may write things on the bulletin board, they may see information, take in information from the TV, they may send and receive mail in our mailbox, and they may make phone calls to the outside world. They have to get their work done in here quickly and leave so the next person can come in and do their work. Otherwise, if they sit in the room all day, nobody else is going to get their work done, and these are going to be very unhappy people. So how multitasking works: one person gets done with their work, and the next person comes in, does his work, he leaves the room, next person comes in, leaves the room, and then the purple guy comes in. And we just keep doing this all day. So for humans, naturally, this would be would not be very workable in the real world. You couldn't do this, but this is really just a metaphor for how multitasking works in a microprocessor. And let's just ignore for the moment modern microprocessors that have multiple cores where multiple things can get done at the same time. We're going to keep things simple and talk about the Arduino, or if you're familiar with microprocessors from the 1980s like the 6502 or the Z80, that's what we're talking about here. So the microprocessor here, the metaphor really for this is the room. Only one thing can really be executed at a time, and although a system like an Arduino can give the illusion of multitasking, in reality there's only really one thing going on at a time. There's only one instruction, one subroutine that is executed at one given time. The smiley people here, smiley faces, are metaphors for processes or subroutines. In a larger computer system like a Windows server or a Linux box, we call these processes. In an Arduino, we can use subroutines or C functions as processes. Within the microprocessor, there's various amenities in this room here. The bulletin board, you can think of that as global variables. We can read and write variables. As people are working in here and they write something on the bulletin board and they leave, somebody else comes into the room, they can see on the bulletin board what was written there. So maybe the yellow guy wants to give a message here over to the blue guy. He'll write something on the bulletin board for that blue guy. But that's really the only way that they can communicate in here, is by looking at that bulletin board. The other devices here, TV, mailbox, the phone, they're like our I/O lines, the serial port, perhaps I2C devices. when people are working in the room here, they may want to receive messages, they may want to send messages. So the mailbox in the Arduino context is kind of like the serial port. TV, maybe you can consider that like a sensor, like a Hall effect sensor or an accelerometer or a compass or something. You have information coming in that the person can see and do something with, maybe write something in their notepad or write something on the bulletin board. A phone, that could be like I/O or an I2C bus where we can send data in or out by speaking on the phone, or I guess maybe if it's a smartphone, you could send a text message or something, and that would be analogous to an I2C bus. The notepad in this metaphor we have here is the local variables within a subroutine or a function. Each guy here has their own little notepad. They've got their own local variables, or each function or process has their variables that they know about in their notepad. They can't give that notepad to anybody else, but they keep this so they can keep track of what they did and what they want to do and what the current state of their work may be, so that when they leave this room and they come back in again, they can look at their notepad and see, oh, okay, I got this done, but I need to do this thing now, and I need to do that thing. So it keeps track of what they're wanting to do when they get in this room. And then when they leave the room, they can't do anything. They can't do any work. They just sit there with their notepad until the door opens again and they can get back in and do their work. Now that we've looked at this rudimentary metaphor for multitasking, let's look at some code. Now, I promise we're not going to spend our entire time in this series learning how to make LEDs blink. However, this first example here is a good place to get started, as everyone in Arduino programming has started with the venerable blink sketch. In this simple sketch here, we're going to blink 3 LEDs sequentially: a red LED, yellow LED, and green LED. We have the defines up here for the pins. We initialize the pins in setup, nothing fancy here. And then in loop, we just infinite loop here, turning the red LED on, off, yellow on and off, green on and off. And in between here, we're doing a delay of 1,000 milliseconds. Very simple. This sketch behaves much as you would expect, blinking the LEDs. The problem with coding like this is these delays in here. And anytime you see a delay, that's really an enemy of doing multitasking, because when you're in this delay here, nothing else is getting done. The microprocessor is executing no operation, an NOP code. So this is really wasted time. This is time that we could be doing something else. If we just want to blink 3 LEDs, the sketch is perfectly fine. But if we want to do some real work, get some real things done, there's much better ways to code this. Here's our blink sketch again, but done in an entirely different way, a way that's going to allow us to build upon this and multitask. As before, we have the 3 pins defined for the 3 LEDs. What I've done here, I've taken the code out of setup and loop, and I'm calling functions. This not only makes your code look cleaner and easier to follow, also gets you in the mindset of making things more modular and being in that multitasking mindset. So I really try to keep code out of setup and loop and just call all functions in here. And I basically within loop, I treat every function as a process. Here in setup, I call initialize pins. It's very simple. We go through this once, just setting up the pins as outputs, and I make the red LED, go high. I turn it on. And then in loop, we execute service LEDs. That's all loop does, is just call service LEDs. Here's where the magic really happens then in the service LEDs function. We have 2 variables, static variables. You may not have dealt with static variables before, but what they do, there are local variables that do not lose their value when you exit the function. Normally, when you execute a function, the variables are created. When you enter the function, they're used within there, and then when you exit, those local variables are wiped away and the values that are stored in them are gone. Static tells the compiler to make them variables that will live on after we exit from the function. So these are essentially like in the example that I had done before with the people in the room. These are like the notepads. This is your state information. We're basically making a state engine here where we're keeping track of things that are going on, keeping track of the state of items within this process or this function. So we've got one to tell us what LED is currently on. And what I'm using is the defines up above for the pins. I'm reusing them as a state variable value. So I'll use LED red, LED yellow, and LED green as values in this byte here. So this is recording what LED is currently on at the time. If you recall up here in initialize pins, we turned on the red LED initially. So we know the first time going into service LEDs, the red LED is already on. So I'm initializing that value there to say red LED is already on. And then I also have here an unsigned long variable, static again. It's going to save the value as we exit the function. And this will be recording the time in milliseconds that we last made an LED transition, that we changed from one LED to the other. The Arduino maintains an internal clock that you can access via the millis function. So we're going to use that to tell where we are in time. We're going to store that in this static unsigned long variable to record each time we do an LED transition. So what we do here, we look at the last LED transition time, and if 1,000 milliseconds, or that's 1 second, has passed, we go into this code and we switch which LED is on. So we're taking the current clock minus the last time we did the transition, and the difference of that will tell us the time that has elapsed since the last LED transition. We look at our state variable, current LED on. That tells us what LED is currently lit. And if we currently have the red LED lit, we turn that off and we turn on the yellow. If the yellow is lit, we turn off the yellow, we turn on the green. And for the green, we turn off the green LED and then turn on the high, and the cycle repeats itself the next time around. We change the state variable each time. We record that the yellow LED is on. Here we record that the green is on. And here we record the red being on. Now after we make the switch, we have to make sure that we record a transition, or the transition time, so we update this state variable, last LED transmission time, with the current clock, so we know when we made our last transition. So you see no delays in this function here. We come in, we look at the clock and see if a second has passed since the last time we made the change. We see which LED is currently on. We flip to the next LED. We update our little notepad or local variable or state variable and say what time we made that transition, and we exit and we go back to loop. So at no time are we sitting around doing nothing. We're constantly checking the clock. Now that in and of itself consumes time, but we're really only doing any heavy lifting once every second, where we change the LED and we set some variables, and this really takes microseconds to execute. So there is a lot of CPU time left that we can go into loop here, and we can do other things within loop, other processes. We could add another function in here, do this, do that. This could be things like updating a LCD display, servicing a serial port, looking at the state of I/O pins, and doing all kinds of things. And I'm going to go into this in more detail in subsequent videos. Understand this simple sketch, how this works, and the concept of making everything modular and doing timing without doing delays by looking at the clock, looking at millis, seeing how much time has passed, and doing things based on that clock and not doing delays. This is a big step going forward in being able to do better programming and doing multitasking in an Arduino. I hope this video helps you out, and I hope you join me for subsequent videos where we do more coding. Take care.